So let's solve today's quiz question. This was the cheapest quiz, the easiest quiz we have experienced so far. But once in a while we should have those cheap quizzes so that your quiz average goes up. But what does the question tell me? It tells me there's a mass. I'm not given what the value of that mass is. There are two forces acting on it. There is one F1, which is given here. Probably not, I did not plot it correctly, but some force. And then there is another force, F2. And it's moving with constant velocity v, which is also given. So the question is, what's the second force? And how do we solve it? We say, hey, if this particle is moving with constant velocity, it means the net force acting on it, which we called F net, is 0. Why? Because of Newton's first law. Or you could say, because of Newton's second law, if velocity is constant, acceleration is 0, net force must be 0. So whatever the value of velocity is, does not matter for us. This was just given as a red herring. It's just to lead you away from the correct answer, right? And I know that if there are two forces, F1 plus F2 must be 0. So F2 must be, even my plotting should just cancel F1. Right? F2 should be minus F1, which is minus 2 newtons I hat plus 6 newtons J hat. That's it. Okay? Good. That was super simple. You'll never get questions like that on the exam. But well, nonetheless, it's good to check it once in a while. Let's make sure that we conceptually understand what's going on. Good. Now let's talk about applying Newton's laws and solve some examples today. So let's solve one of the best examples. If I have a pulley with mass m1 and m2, which is tied to some fixed place to the ceiling, and let's say that's a frictionless, massless pulley, and again, this is a massless, inextendable string. So I take a piece of rope, tie two masses to both ends, and hang them by a pulley. So the question is, and this is all under gravity G, what are the acceleration of the masses if the system is let go from the position shown in the figure. Now, first of all, let me talk about these assumptions. We'll assume, until I instruct you otherwise, we'll assume that all of our pulleys are frictionless. So they can rotate without any friction. All right? What does that essentially mean? It means the rope that's passing over them, the string, has constant tension throughout. Okay? Whatever is the tension on one side of the pulley, it's the same on the other side. So I will not repeat. I'll draw a lot of pulleys. I'll never repeat this assumption. So don't worry about it. When we talk about rotational motion in more detail, we'll talk about what to do about if there is a friction in our pulley, if our pulley has a mass. Okay, we'll be able to handle that. But let's right now take the simplest possibility. And for all our strings, all our ropes, we'll assume two things. First of all, their mass will be much lighter than the masses involved in the problem, so I can basically neglect their mass. I'll treat them as if they are massless. All right? And I'll also make sure they are strings, not springs. They are not elastic. They do not, if I put tension on them, they do not get longer. All right? So they are not bungee jumping cords, but more like halat, right? So it doesn't extend. Now, let's solve this. How do we solve any kind of mechanics problem? So, first of all, I'm asked to find the accelerations, but let me make it a little bit more interesting. This is the first question I'm asking. The second question I'm asking is, what is the tension in the string tying the pulley to the ceiling? Tension over here. How do we solve mechanics problems? We have to use Newton's laws. How do we use Newton's laws? Remember my comment about Newton's second law. It's valid for point masses, okay, or rigid bodies. So what I need to do is I need to identify all the moving parts in this problem, all the masses that move in this problem, and apply Newton's second law to each one of them systematically. Okay. So here I have M1. Let me show it just as a point. What are the forces acting on M1? There is always, almost always, gravity pulling you down, M1G. But there is also another force, which is the tension in the string going over the pulley. So will be T. I need to do the same thing for M2. What are the forces there? M2G is down and T is up. And then I need to decide how this system moves. Well, I don't know. I have not been given the values of M1 and M2. But I should assume, I can assume any direction of motion. All right. Let's say I'm assuming M2 goes down with acceleration A and M1 goes up with acceleration A. Okay. So in my separate diagrams, which are called free body diagrams, M1 is going up with A, M2 is going down with A. Why do they have the same acceleration? Because they are on the same string. If M1 moves up by a distance x, M2 moves down by a distance x, right? So if I take one derivative, whatever is the velocity of M1 going up must be the same velocity of, well, speed M2 going down. If I take another derivative, whatever is the acceleration of M1 going up must exactly be the same acceleration for M2. All right, that's why, because they are on the same string, they must have the same acceleration. Is that point clear? It looks very simple, I know, but we're going to make things complicated, so let's get the basics right. Now, the diagrams where we show forces acting on the masses and their accelerations are called free body diagrams. Okay. And this is the accepted and trusted method of solving mechanics problems. You're going to use it, and nowadays you can actually write some software to solve larger mechanical systems. So you want to simulate the larger mechanical system. How do you actually do this? You must supply an algorithm to your computer to solve this mechanics problem. This is the algorithm you supply. You say, for each small piece in your whatever mechanical system you have, you write Newton's equations separately. So free body diagrams, plotting these diagrams and solving for Newton's second law in these diagrams is an algorithm to solve all kinds of mechanics problems. Okay? So we expect you to show these free body diagrams in all your solutions. Okay, so for the first mass, what is M1A? A is upward, so it must be T minus M1G. How about M2? What is M2A? Because it's moving downward, this is going to be M2G minus T. Okay, so what am I supposed to find? I'm asked to find A. So here's what I'll do. This is my first equation and this is my second equation. Let me add them. If I add them, on the left hand side I have M1A plus M2A equals T minus M1G plus M2G minus T. The tensions cancel. So that gave me M2 minus M1G. And here I have M1 plus M2. So the acceleration of the system is M2 minus M1 over M2 plus M1G. Here's a point where a lot of first-year students have trouble. They keep asking, hey, how did we know that M2 will go down and M1 will go up? What if actually M1, let me supply a numerical value now. Let's say, let's say M1 is 2 kilograms and M2 is 1 kilogram. Intuitively, I know that my acceleration should be in the other direction because M1 is heavier now. I showed my acceleration to be, for M1 to be up, right? Is that a problem? Well, it's not. Why? Let's put in the numerical values now. A would be M2 is 1 kilogram, M1 is 2 kilograms, and here I will have 3.0, and let's take G to be 10 meters per second square. So what will that give me? Minus 3.3 meters per second square. Aha, that's great. My formula, once I do it, all my equations consistently, gives me the correct result. I will find my acceleration is minus 3.3. In which direction? In the direction I have shown. Okay? So minus 3.3 in the up direction means 3.3 in the down direction, which is the correct way that M1 would move. Okay? Is that point clear? Once you're actually assigning these accelerations consistently and apply Newton's laws consistently, the answers you find will be correct for all kinds of masses. One way may be larger than the other. The whole system may be moving opposite to the direction that you actually assigned your velocity. Nonetheless, your equations will take care of that. All right? So you don't have to guess which way things are moving if you apply Newton's equations correctly. All right? Good. I had one more question. How about the tension in the rope tying the pulley to the ceiling? Well, for that, I'll do something strange. I will actually, let me get a better color. So I have this pulley which is tied to the ceiling with a tension T2. What other forces are there acting on this pulley? The tension in the rope that's going over the pulley. So it's trying to pull it down. Is this pulley accelerating? Its acceleration is 0. Its mass is also 0. Right? So that's very good. Which means m times a is 0. That must be the sum of all these forces, T2 minus 2T, which means T2 must be 2T. But I need to find T then. How can I find T? The same equations I have here, I've added them. I could have also subtracted them. The first equation minus second equation would be m1 minus m2a would be T minus m1g minus m2g plus T. Right? So let me rewrite it over here, or let me do a trick. Okay. So I'm solving 2t is equal to m1 minus m2a plus m1 plus m2g. But let's remember what a was, m2 minus m1 times m2 minus m1 divided by m1 plus m2 times g plus m2g. That is equal to 2t, which is equal to what I actually asked, t2. So that, what does that give me? Let's see. I have m1, m2 minus m1, so it's going to be minus m2 minus m1 square divided by m1 plus m2 plus m1 plus m2 times g. So all in all, m1 plus m2 square minus m2 minus m1 square divided by 1 plus m2 times g. This is really nice. If I open it up, m1 square 2 m1 m2 plus m2 square minus m2 square plus 2 m1 m2 minus m1 square divided by m1 plus m2 times g. These two m squares cancel. That cancels. Overall, I have 4 m1 m2 over m1 plus m2g. That is t2. Okay. I also found a above. What was it? It was m2 minus m1 divided by 1 plus m2g. So, did I reach my goal? Yes. Let's check the units. What should be the unit for the tension in the rope? It should be newtons, right? It's a force. So let's check. What do I have here? The unit for T2. 4 does not have any units. What's the unit for M1? Kilogram. I have another kilogram. Here it's kilogram square. M1 plus M2, what's the unit? Kilogram. How about G? meters per second square. So I have kilogram meters per second square, which is Newton. So that's good. How about the acceleration on the left-hand side? Well, I have mass in the numerator, mass in the denominator. Kilogram cancels kilogram. A and G must have the same units. They have the same units. So units are also fine. How about some limits? And here's a very simple limit we can think about. Exactly. So what happens if m1 is equal to m2? What do we expect? What should be the acceleration of the system? Well, okay. If my initial velocity was 0, I would expect the system to hang in the balance. If there was initially a velocity v, what would happen? It will just be a constant velocity, right? So, in that case, what do we expect acceleration to be? 0. Does that give me acceleration equals to 0 when m1 equals m2? Yes, it does. So that limit checks. What would be the tension T2 in that case? Well, I'm carrying both masses with that T, right? They are not moving. So I must be handling all the weight on that small piece of rope. So T2 in that case must be exactly equal to 2mg. Let's see if it's equal to 2mg. T2 is 4 times. Both masses are the same. This is m squared. Divided by m1 plus m2 is 2m. M's cancel 2mg. So that limit is also correct, which means probably I've actually found the correct result here. Question?
Could we use for the solving of this problem just the first equation?
Just the first equation.
Yes. Because we get
this one.
Yes.
How would you now? How many unknowns do I have here? I don't know A. I don't know T. So I have 2 unknowns, which means I need at least 2 equations. Okay. So this is going to be the case in all our problems. If we have n unknowns, we need at least n equations to find them out.
But we've solved it for A.
Once you have solved for A, and for that you had to use equation 2, then you could just plug in A here and find T. That you could definitely do.
There's an easy way to find T.
Okay.
We can equate acceleration of both equations and then find out T and then.
That would also work, but be very careful. Be very careful. If, and that would work in the special case, but if I actually put in moving pulleys, then such an approach would not work. Okay, that's why I know there are, at least for such simple problems, methods which will give you the question, which will give you the solution more quickly. Please do not use them. Please try to stick to the algorithm, because as things get harder and harder, those methods will fail and you will not know where they will fail, while this method of drawing free body diagrams and applying F equals to ma would work in all cases. All right? Questions? Comments? Isn't there a comment? Question? You were talking, so maybe. Is that something important? Okay, good. Now, good. This was really simple. Let's solve one more simple example. If I actually have three masses on a frictionless surface. All right? The question is to find what T1 is. What's the tension in the rope tying M2 to M1. All right? So that's the only thing we need to do. Now, how do I solve this? I'll keep asking the same question and giving the same answer. I'll have to draw the free body diagrams for all the masses involved in the system. Okay. Some students tell me that they feel dumb, going through the algorithm. They say, hey, I can solve this more quickly. But please try to stick to this algorithm. Because questions will get harder and harder, and you will see that the algorithm works every time. Okay? Right now, you can probably write down the result without much problem, but let's stick to the algorithm. So, what are the forces on M1? There is always M1G, but is that mass going down into the table, or is it jumping off the table? No, we do not expect any motion in the vertical direction, so there must be a normal force N1 which exactly cancels the gravity. And what else does it feel? It actually feels tension. Let me call this T1. And the tension in the second rope, T2. So how about M2? So this was M1. How about M2? Again, I have M2G, which is cancelled by N2. What are the forces acting on M2? There is the rope pulling it right, but there is also the rope which is pulling it to the left. And why are these two tensions equal? You can give two answers. One is they are connected to the same string, right? It's the same mass as string, so it must have the same tension. Or you can say, even if that there was some sort of strange mechanism between them, maybe they were electrically charged. They do not have to pull each other with strings. They were maybe pulling, one is positively charged, the other is negatively charged. They are pulling each other by electrical forces. Still, they would feel the same force because of Newton's third law. Great. So, how about M3? Again, I'll have a normal force which is cancelling M3G. Now I'll have the force F which is acted upon, which is the given quantity. And now T2 is pulling it left. And here comes the next step. Now I must decide the accelerations of the objects. How are the accelerations related to each other? In this problem, it's really simple, right? I mean, if M3 is accelerating with A, it must be carrying M2 with the same A. Why? Because if they had different accelerations, the distance between themselves, the relative acceleration would be non-zero, which means the distance between them would be extended or getting smaller, right? But that's not allowed because I have a string between them. Okay, so the accelerations must be the same. It's also intuitively it makes sense. I hope by next week you'll understand why I keep emphasizing that point. So all three masses have the same A to the right. And Newton's equations are M1A is just T1. Why did I not worry about N1 or M1G? Because my acceleration is clearly in a perpendicular direction to the normal. Those normal forces are just cancelling each other. For the second mass, I have M2A, which is equal to T2 minus T1. And final case, M3A is F minus T2. Now, how many unknowns do I have in this equation? Let's count. Let's see how many unknowns I have. A is an unknown. So 1. T1 is an unknown. And T2 is an unknown. So I have 3 unknowns in my problem. How many equations do I have? 1, 2, 3, which means I can actually solve for all the 3 unknowns. I can determine all the 3 unknowns. And in this case, it's going to be simple. If I add up all these 3 equations, 1 plus 2 plus 3, on the left-hand side, I'll have M1 plus M2 plus M3 A. On the right-hand side, I have something really nice, T1 plus T2 minus T1 plus F minus T2. T2's cancel, T1's cancel. So apparently, the acceleration is F divided by M1 plus M2 plus M3. And what is T1? T1 is just M1 times A, which is going to be M1 times F divided by M1 plus M2 plus M3. Did I reach my goal? Yes. What was asked? T1 was asked, and I found it in terms of given quantities M1, M2, M3, and force. Does it make sense unit-wise? I expect T to have units of Newton. Force has units of Newton. I have a mass multiplying force and mass dividing the force, so units also check. And how about the limits? What should be the tension if M2 and M3 were 0? M2 and M3 did not have any mass. In that case, M2 and M3 would just become parts of the string, right? They'll be massless. They'll just take the force to M1. In that case, so M2 equals 0, M3 equals 0, T goes to F, and that limit is checked. So most probably we have found the correct result. All right? Let's solve one more example. Do you have a problem seeing this color? Should I use it or? Okay, good. So let's ask for one more example. So, the inclined plane is fixed to the floor. There is no friction. All my pulleys and strings are massless and frictionless. There is gravity G. So now I have 2 questions. First question is, yes, I need to also supply the angle. That's very good. Thank you. Find, I'll also give the height of M1 from the floor, find the time it takes for M1 to hit the floor. Second question is, what is the magnitude of the force the floor is applying to the inclined plane? So, comment. It's not given, but it's not moving. It's fixed to the floor, so we don't need to know its mass. Okay. I understand what you mean. I'm just talking about the horizontal force, but let's give it an inclined plane, okay? Now, how do I solve the first part? First of all, let's forget about the inclined plane. It's a part of the floor, okay? So what are the only moving parts here? I have M1 and M2. So what do I need to do? I need to draw the free body diagrams for M1 and M2, all right? Good. So what are the forces on M1? There is a single string going out through the system. So there must be a tension, the same tension throughout the same string. So what are the forces on M1? I have T and I have M1G. Now, the second, so it's like a point here, right? The second part, the second free body diagram is actually a little bit harder. So for M2, this angle is theta. What are my forces? There is a tension force like this. So, and that tension force is making an angle theta with the horizontal. There is M2G. How about the force that the inclined plane is applying to M2? It's called the normal force. What does normal mean? Normal means, of course, normal, but it also means perpendicular in the mathematics jargon, okay? So normal means it's the perpendicular force any surface applies to an object on itself, okay? So that force, the normal force, must be perpendicular, okay? So the angle here must be 90 minus theta, okay? Now, I can extend this, right? How about the angle here? That angle is also theta. Why? Because here I have a right angle, and here I also have another right angle, okay? Now, how about the accelerations? Let's take another color. Which way is the acceleration of M1? I want it to hit the floor, so it better go down, okay? So let's call this A. How about M2? Which way is it moving? Well, if I'm pulling the string down from here, the other one must be moving up the inclined plane. So its acceleration must be in the direction of the tension, all right? Now, yes?
How do you know moving towards the floor?
Excellent question. We don't. Do you remember the first example we solved? You were sleeping through that. So we don't. But as long as we are consistent, at the end of the day, our formulas will tell us, okay? If m1 is actually going up, then our formulas should tell us that that time is infinite, okay? Good. So that's one of the limits that we could check. Now, it's the same acceleration because they are tied to the same string. So let's apply Newton's second law. m1a is m1g minus t. How about here? I have three vectors. So what I need to do is to take the components of those vectors. Here, the component in the normal direction and the component, there is a component in the inclined plane direction. The length of the component in the normal direction is mg cosine theta, m2g. And in the inclined plane direction, I have m2g sine theta. Now I get two equations. What's the acceleration in the normal direction? Is my mass m2 jumping off the plane? No, it's not. It's not going into the plane either. So acceleration in that direction is 0 and is m2g cosine theta, which actually doesn't change anything. That's just an extra equation, some extra information. How about in the inclined plane direction? m2 times a is t minus m2g sine theta. All right. So I'll call this my first equation, the other my second equation. Let me add them up. 1 plus 2 is m1 plus m2a. And if I add these up, m1g minus t plus t minus m2g sine theta, t is cancelled. So it's going to be m1 minus m2 sine theta times g. So a is m1 minus m2 sine theta divided by m1 plus m2 times g. We can easily see this expression is positive if m1 is larger than m2 sine theta. Then it's okay. Then I'm sure that it's positive and my mass m1 is going down. But on the other hand, if m2 sine theta is larger than m1, then it's going in the opposite direction and I will never actually reach the floor. So I should maybe write if m2 sine theta is larger than m1, m1 does not reach the floor. Have I reached my goal? Not yet. Find the time it takes for m1 to hit the floor. How do I do that? Now I have found the acceleration here. And the motion will be motion with constant acceleration, right? So this is motion with constant acceleration. One half a t square must be equal to h, the distance that's traveled. So t is 2h over a square root, and I have all the expression for a here, 2h divided by m1 minus m2 sine theta, m1 plus m2, no, g is down. And apparently that's the answer for the first part. Let me quickly do my check. The second part I'll solve in our next lecture. This is 1, 2, and 3. Let's do our checks. First, what's the time Did I reach my goal? Yes, time was asked, I found my goal. But let's quickly check the units. What's the unit for h? Meters. What's the unit for m1 plus m2? Kilograms. What's the unit for sine theta? It's unitless, it's just a number. So m1 minus m2 sine theta is kilograms. How about g? Meters per second square. And I have a square root. Kilograms cancel, meters cancel. It's the square root of second square second. So unit wise we are all right. And there is this excellent limit that we can check. What happens if m2 sine theta is larger than m1? m2 sine theta is larger than m1. Time I find is square root of a negative number. It becomes a complex number, right? That doesn't make sense. So this is great. Okay, my answer already tells me that if m1 is going up, the time it takes is imaginary. It doesn't exist. Right? So that's the power of doing things consistently. I'll see you next week.